So I would like to talk about this paper by Jeremy England, which the title you see here, it's called The Statistical Physics of Self-Replication. So his aim was to apply general physical principles to like biological processes. I think maybe self-replication is not the right word. It should be like irreversible biological processes to get some energy bounds or some thermodynamic bounds based on general principles for certain biological processes. And so I noticed this paper actually this spring when I saw that David Reeb posted a paper where he explains the physics in more basic terms. So the original physics treatment, so not the biological treatment, but the treatment of the underlying physics was by stochastic dynamics, which is like a popular approach in thermodynamics or in quantum thermodynamics. And David Reeb, he derived the same physical equations from like reversible Hamiltonian dynamics. This is what I will show you. And then I will, once this equation is derived, I will switch to the biological part, and this is taken from the paper by Jeremy England. So my aim is to show how maybe by general physical principles one can get meaningful statements about quite complicated processes. And so I mean there's some hand waving, but I think it's still interesting enough to talk about it. So the basic setup is that one has two distinct or maybe like situations, let's say, which I call 1 and 2. And they are, so each one of those is described, as a subset of the phase space, so of the microscopic phase space of a system of interest plus a bar. So each one is described as a subset which I denote by P1 or by P2 of the phase space of the full phase space of some system of interest plus a bath. So the process that I'm going to talk about, they occur in the presence of a thermal bath at some temperature. I'll make an example soon. So maybe we assume that everything happens at constant energy. So the second assumption is that we have reversible dynamics. So all the dynamics that is happening on the system and on the bath is governed by Hamiltonian or by like classical mechanics, Hamiltonian dynamics, which happens on a shell of constant energy. So these subsets of the phase space should be subsets at a constant energy of the phase space. Okay, let me give you one example of a situation that I'm thinking of, or that is treated in the paper. So one of the examples is there is a container which contains water at some temperature, and this water contains some nutrients which are necessary for and it contains a single RNA molecule which is in the process of dividing into two RNA molecules. So let's assume that the full situation is such that this RNA molecule is ready for this process of ligation to happen. Okay. I'm not at all, basically I don't know about the biological background of this, but well, I hope still you can like imagine what the situation is. So there is some biochemistry process which will lead to a different configuration where there are two RNA molecules. So this is a replication process. And there's still water everywhere. and there is now a different arrangement of nutrients. So some nutrients have been consumed in the process in order to like arrange the internal structure of this molecule such that it would split into two. So there are some nutrients, and maybe this process produces some other products, like in the chemical reaction that is going to happen. So and all of this happens in a reaction time, which I call by tau, which I denote by tau. Okay, so what is the system and the bath here? So the system would be this. All the degrees of freedom like that are contained in the RNA molecule and in the nutrients, or in the 2-RNA molecule and in the nutrients. And in the final state, there are also the products. And the bath is basically the water at temperature 1 milliliter. Okay, so this would now be the situation 1 and the situation 2. And I mean, although these situations are very, very complex arrangements of like the basic atoms or the basic degrees of freedom, one could still think that the whole system is described on a classical phase space, and just there are some number of points in the phase space which you would call they correspond to situation 1. So there are some macroscopic arrangements of the molecules which you would like microscopic arrangement of the molecules, which you would macroscopically say there's one RNA molecule and a certain amount of nutrients, and there's some other points in the phase space. So this would be all the points in the set P2 of the phase space, where you would say there are 2 RNA molecules and some other arrangement of nutrients which would correspond to the final state of such a reaction.
So what's the dynamics here? I mean, is there interactions between the molecules and is there interaction?
Well, so the idea is that the full system is closed, so system plus bath is closed, and there is a Hamiltonian dynamics acting on it, and I will tell you about 2 more specific assumptions on the dynamics in a minute. Okay? But the basic idea is that this process is not driven from the outside, it is just happening by like autonomously. There is just a Hamiltonian interaction. I'll tell you a bit more about the specifics in a minute. So this is the basic setup.
And the bath is assumed to be finite? Or?
It's assumed, so in the computation later I will make like some assumption which only work if the bath is very large. Like equivalence of microcanonical and canonical or something. Okay. So, and in what is very important for biological processes is that even though the underlying dynamics is reversible, like Hamiltonian, there should be a definite direction in which the reaction happens. So, of course, I mean, it's biologically advantageous for RNA molecules to replicate than to decay, for example, right? So the basic, what one basically wants is that the probability of this process to happen. So, given that you are in a microscopic arrangement which corresponds to situation 1, the probability to go from there to some microscopic arrangement that corresponds to situation 2, this should be much, much larger than the inverse process. Right? So there should not be an equilibrium between these 2 situations. Right? So basically, I mean, so this means the process should be irreversible. Process should be irreversible. And what I will now do is to introduce 2 more specific assumptions, and then to derive bounds on the energy consumption of such a process, given that one wants this irreversibility to happen. So that on the macroscopic level, this transition is much more likely to happen than the reverse transition.
So this is an assumption, irreversibility.
No, I mean, this is not an assumption. I mean, in the final formula, there will just be the ratio of both quantities appearing, but this is what I have in mind. 2 situations, like two situations where this transition is much more likely to happen than this transition. Okay. So I mean, I hope this is well motivated by this biological example. All right. So in order to derive a quantitative formula, this paper makes, or like especially David Reeb's derivation makes two more assumptions. So assumption 1. Assumption 1 is that these two regions of the phase space are invariant under time reversal, and the Hamiltonian is also invariant under time reversal. So the reversible dynamics is, let's say, given by a classical Hamiltonian H. There's also a quantum treatment in this paper, but I will maybe comment on this in the end. So they are invariant under time reversal. So what does this mean? One can really write it down in very microscopic terms. So this means that if some arrangement of momentum and position vectors is contained, for example, in this phase space subset P1, then I also demand that the same configuration with reversed momenta is also in this subset. The same I demand of this here, and I also demand that the Hamiltonian has this structure, like it's 1/2 P transpose times some mass matrix times P plus a potential which just depends on the, I mean, this would be one situation which covers this. So basically it means that in the definition of my situation, I should only care about the positions of all microscopic constituents, not about their momenta, which is kind of a plausible assumption. So if one puts this first assumption, then I would like to show you that one can already derive some relation between those two transition probabilities. All right? So let me show you this, because I think it's quite interesting that from this assumption one can already derive this. So let's write down the probability that if one starts in a microscopic arrangement belonging to the phase space volume P1, what is the probability to go into the phase space volume 2 after some time tau? So we can just write it down abstractly. This is the integral over the phase space, given that we start in the subset P1, and that if we evolve the situation P2 back in time for a time tau, so we do the Hamiltonian time evolution for time minus tau of this set 2, then we should be in a configuration. So I mean, all configurations that are contained in this set, they will lead to the situation P2 after the time tau, right? So this is the volume of all configurations that start in 1 and end up in 2, and because we want the conditional probability, we just divide this by the volume of the P1 space. So, and because of this reversibility of the interaction, it doesn't actually matter whether we evolve forward in time or backward in time, just because of these two assumptions. So this is the same as evolving the phase space volume 2 forward in time. Now, because of Liouville's theorem, the phase space volume is actually invariant under time evolution. So I mean, we can just evolve this here again backward in time. So this is the same as ft minus 1 P1 intersected with P2. So now I just applied the time evolution for time minus tau to both sets. This leaves, according to Liouville's theorem, the phase space volume invariant. So, and now you see that if I write down the reverse probability, the probability that if I start in 2, I will end up in 1, I exactly get this here. So this is this integral P2 intersected with f to the minus tau P1. I mean, just analogously to this, but it's actually just that integral. But now the normalization factor is, I know that I already start in configuration 2, so I would divide by the volume of the phase space 2, right?
So, sorry, what is F?
F is the time evolution operator. So like one can also formulate this quantum mechanically, but let's say that we are in classical mechanics, right? If you solve the Hamiltonian time evolution equation, it tells you that if you are at time 0 at a point p, q in phase space, then you just evolve the Hamiltonian time evolution for a duration of time tau, and after this you will be at a point which I denote by f to the f tau applied to this point, right? Does this sound familiar? Okay, so now the numerator of both expressions is the same. So what one can kind of derive, one then has the following relation, that the probability to go from 2 to 1 divided by the probability to go from 1 to 2 is, because the numerator cancels out, is just equal to the phase space volume of the region 1 divided by the phase space volume of the region 2. Alright, so this is quite a simple formula. If one has time invariant dynamics and setups, then the probability, the ratio of the probabilities of going from one situation to the other just depends on the volume of the corresponding phase space elements. This comes just from this here.
So a stupid question, if you divide these two things, then isn't that 1?
No, because
Yeah.
here I normalize by the phase space volume 1,
Yeah, okay.
and here by the phase space volume 2.
Okay.
This is clear?
Mhm.
Okay, so now, so far everything has happened in the microcanonical picture, kind of where we really keep track of the microscopic positions and momenta. And now the second assumption will allow us to go from this microcanonical ensemble kind of to the canonical ensemble, to continue with the computation basically. So the assumption 2, which is the last assumption necessary to derive the final formula, is that these situations, so these situations 1 and 2, are what is called metastable states. Metastable states, so what is this? This means that if we are in a microscopic configuration contained in this part of the phase space, then the dynamics will remain in there for a long time, and the dynamics will actually be ergodic within this phase space volume for a long time. So you should think that, for example, this configuration could be a configuration of like H2 molecules and oxygen molecules, O2 molecules, which I mean, this is of course not a stable configuration. I mean, there will be this reaction where they combine to water, but at room temperature, the configuration of having separate hydrogen molecules and oxygen molecules is quite stable. So for a long time, this will be a stable configuration.
But then when the transition would happen from 1 to 2?
Mm-hmm. So, okay, let me just write it down in more detail. So I assume that the dynamics is ergodic within within this volume 1 and also 2 for times which are smaller than the transition time. So I assume that this macroscopic transition happens on a time scale tau, but I assume that the dynamics within these regions of the phase space is much smaller. So I assume that if one is at a point in the phase space corresponding to the situation 1, then the dynamics will equilibrate on time scales which are smaller, but of course on longer time scales I want this transition to happen. Okay, so I mean this leads, if one has such metastable states, then one can sensibly talk about entropies. I mean, entropies for really unstable states are not well defined because, well, I think that this is a frequent issue in non-equilibrium thermodynamics. And it also means that if the dynamics is ergodic within these regions of the phase space, then you can think of, for times which are smaller than tau, you can think of this phase space volume P1, you can think of it as a kind of a closed system which equilibrates in short times smaller than tau. So this means that we can use the equivalence between the canonical ensemble and the microcanonical ensemble restricted to these phase space volumes P1 and P2. I mean, I think this assumption is very reasonable because if you have such a situation where you really can observe one RNA molecule and a certain amount of nutrients over time, this means that this situation, although it is not completely stable, after some time tau, it will evolve into some different configuration. You can make this observation of that this situation exists, so it must be stable over a kind of short time. That's what I mean by metastable.
And this metastability assumption, the temperature remains fixed the whole time, right?
Yes, temperature remains fixed. So this means that there is an equivalence between microcanonical and canonical ensemble. So then one can continue this computation. Basically, I mean, so one can take the logarithm of this ratio of probabilities and I mean one can write this. I mean that's what's written up there. It's the ratio of the phase space volumes. And now instead of taking like the microcanonical phase space volumes, one can take the canonical phase space volumes. Let me write down one formula, but I will not give you the whole computation. So there's something similar in the denominator. So basically the phase space volume corresponding to the situation 1 would be given by an integration over the bath degrees of freedom and the system degrees of freedoms. And an energy term which gives the energy of the system depending on the configuration of the bath. And if you then compute a little bit, then it's not too hard to imagine that you can get the following result. So you get the entropy of the system in configuration 1 minus the entropy of the system in configuration 2. So there are appropriate definitions of these entropies which make this an equality. I won't write them down. Minus beta delta Q. Okay, so this is the heat, this is the energy transfer to the bath. And I mean, I think what we would write down that this is the entropy of the system given the bath degrees of freedom in the microcanonical ensemble described by of situation 1. Right? I mean, how the energy comes in is by this term. This is the energy of the system if the system is at configuration X given the bath configuration Y. Right? So anyway, all I want to say is you need this equilibration assumption to be able to compute something, and so the final formula will be, so the final result will be that the entropy increase of the system plus the heat transfer to the bath divided by the temperature. So this is just equal to the logarithm of the probability of this transition divided by the probability of the reverse transition. All right. So this is an equality. So what does it mean, or why is it plausible that you get this formula? So if you again look at this example, somehow the situation 2 has more structure than the situation 1. I mean, it contains 2 RNA molecules, whereas this here only contains one such ordered RNA molecule. somehow it has more order in the system, but maybe the water actually has more entropy in the second situation. So we want that this is big. Want this big. So this means that we need that the volume of the second of the phase space that describes situation 2 is much bigger than the volume of the phase space of system plus bars that describes situation 1. So if we want that this process happens in a stable way, so that this probability is much bigger than this, then of course, I mean, we can either yes.
This also affects the entropy as well. S2 would be bigger later than S1?
It doesn't necessarily need to be.
So it can be negative in this.
It can be negative. I give you an example later.
Okay.
So if you want this process to happen in a stable way, so that this probability is bigger than this one, this can only happen if either the system is more disordered or you dump entropy and therefore energy into the bar. This is basically, I mean, the intuition behind this. Let me give you 2 examples. So I guess this is the main theoretical result, which is by David Reeb, and I mean he himself says that this is not a completely rigorous derivation, but I mean, given that we have so complex systems, we should only use very general physical principles. So let me give you 2 examples. So example 1, RNA replication. So this would be this example which I drew here. So in this case, one can see that the probability of the desired process to happen, so the probability of the splitting of the RNA molecule is, I mean, proportional to the growth rate, and the growth rate is observed to be like 1/1 hour. In optimal conditions, you can actually perform this process in the lab, and you will see that the doubling time of the RNA molecule happens at optimal temperature and with the optimal nutrients in about 1 hour. Whereas this probability here, you will actually never observe this process. I mean, nature has made this process so stable that you will never observe this process. But in his paper, England gives like a plausible upper bound to this here. So based on the fact that RNA molecules dissolve in water much faster than the reverse process to happen, I cannot really give you all the biologic arguments, but he derives an upper bound on this, which is something like 4 years, which is based on some hydrolysis processes. I mean, I think if one wants to use this formula, one always will have difficulty in estimating this quantity because this is not measurable. This process happens so rarely that you actually cannot measure it. You need to find a plausible upper bounds. So if you measure this, and also I think that there is some argument that there's actually not much entropy change in the system. So this process will absorb some like hydrogen, oxygen molecules and emit some carbon dioxide, but basically the entropy change is estimated to be 0 during this time. So if one takes all of this, then the heat expense is greater or equal than if you have 1 mole of RNA molecules times the inverse of beta, which is equal to kBt. I can't tell you at the moment what the temperature is, but it's in the paper, times the logarithm of 4 years divided by 1 hour. So if one has an upper bound on this probability one has to estimate, then one gets a lower bound for delta Q. So this is what is written here. This is equal to 7 kilocalories per mole, and one actually one gets delta Q is approximately 10 kilocalories per mole. So it seems that the thermodynamic constraints are almost so strong that they give the actual energy expense of this process. All right. If one would have DNA molecules, then they have a much larger half-time. So for DNA, this is about like 1 billion years. It doesn't affect the result very much because you take the logarithm. So for DNA, this here is about 20 kilocalories per mole. But this is already more than the actual energy expense of this process. So, I mean, maybe these principles kind of explain some rough features of the biology. There's another example in the paper about the E. coli bacterium, and they are the factor by which the theoretical and the experimental result, they are off by a factor of 6, but in this case, it's much harder to estimate this probability apparently. So I don't know how credible this is, but I found it interesting that by simple physical principles, one can treat like complex situations.
Okay.
Thank you.
Any questions in the train? Change over to the other board.
What process do they consider when they talk about bacteria?
So there, in order for an E. coli bacterium to replicate, it has to form about like a few billion peptides have to be attached to some, I don't know, and so basically all the bounds they get, so all the terms, this one, and even the estimates for this term, they are based on they are kind of proportional to the number of peptides that need to be rearranged in the process. So right.
So,
I can't.
so if one allows the replication to go forever here, that formula would keep going with the number of replications you do? I mean, is there any restriction on the...
Right.
No?
So I guess, for example, this number, the duplication time for this process is only one, like an inverse hour, only under optimal conditions. And I think if it replicates too fast, then like the constitution of the bath would change and the process will not happen at the same rate. But basically, I mean, if you refill the nutrients and you dilute the RNA molecules, then I guess it will just keep growing. If there's enough space to live. Yeah.